Hello everyone. Again, this is your junior high school math teacher, and in this video, we will continue with the discussion about solving problems involving quadrilaterals. Last time I discussed about solving problems related to parallelograms and its properties. Now in this video, we will have the continuation of another set of problems, but this time we will consider problems related to trapezoids and their properties. So basically, from this presentation, we simply continue what we discussed last time, and you will notice that I discussed the last example of solving problems related to parallelograms. So we're done with this from our previous video. So we will begin with, or should I say, we will continue with example number 5. And from this item, this is where we discuss about problems related to trapezoid and its properties. So let's begin. Suppose you have this problem. The height of a trapezoid is 5 or rather 10 feet, and its bases are 8 feet and 10 feet. So how do we compute for the area of this trapezoid? So let us try to draw a trapezoid and we label those given information. So the vertical segment that you just see from the drawing is actually the altitude. Since it is a segment drawn vertically and it's parallel to one of the bases of this trapezoid, as indicated by the small square drawn at the corner. So we label this as 10 feet based on the given information. And the bases are the parallel horizontal sides. The upper base is 8 feet and the lower base is 10 feet. Now, how do we compute for the area of this trapezoid? Actually, there is a formula for the area of, or how to compute the area of a trapezoid. And that is what? 1/2 the sum of the bases multiplied by the height. So basically, we directly substitute the given lengths or the given segments to this formula, and then we simplify the resulting expression, and that is half of the sum of 8 and 10 times 10, which is the height. And upon computation, we obtain an answer of 90 square feet, and this is the answer, the area of this trapezoid. Okay, we go to the next example or next item, number 6. The area of the trapezoid is 36 centimeters. If the upper base b sub 1 and the lower base b sub 2 are 11 centimeters and 13 centimeters respectively, find its height or the height of the trapezoid. So how do we answer this particular problem? We could first list down the given information and again use the same formula to compute for the area of the trapezoid. And substitute or plug in the given information to this formula. So for the area of this trapezoid is 36, then equals 1/2 of the length of the bases are 11 and 13. Okay, so we plug into this expression for the value of b sub 1, b sub 2, and these are 11 and 13, so that is 11 plus 13. Then we copy the unknown height. This is the one we're going to solve for. This is the one we're going to determine the value from this formula. So we will be doing some manipulations to this equation in order to solve for the value of h. So we have, at this point, 72 is equal to 24h. So basically, we divide both sides by 24 from this equation. And you will notice that we obtain the value of h, which is actually 3. Therefore, the height of the trapezoid uh, in number 6 is actually 3 centimeters. Okay? Next. Now, the diagonals of an isosceles trapezoid are represented by the expression for x minus 47 and 2x plus 31. Find the value of x and the length of each diagonal. Now, since this is an isosceles trapezoid, we need to recall a particular property that we must use in order to solve this problem. And what is that property? Ito yun, no? And that is diagonals of an isosceles trapezoid are congruent. So basically, we equate these two expressions since these are the lengths of the two diagonals of an isosceles trapezoid. So meaning their measures are equal. So 4x minus 47 is equal to 2x plus 31. So we just formed a linear equation in one variable x. So solving for x from this obtained equation, okay, we do some transposition of terms, isolating those terms those terms of x to the left and constant terms to the right. And we combine similar terms at the same time. So we have 2x plus 78. And we simply divide both sides by 2 to get the value of x. And the value of x is 39. Okay? Yun, kuha natin. Now, what about the length of each diagonal? Okay, so we make use their equivalent length, which are both in terms of x. So for one diagonal, having a length of 4x minus 47, so we plug in the value of x here, and that will be 39. So the expression is 4 times 39 minus 47. We have 109 units, which is the length of one of the two diagonals. Now, what about the other diagonal? This time, we use its equivalent expression, so 2x plus 31. So plug in the value of x here. So this expression becomes 2 times 39 plus 31, and we obtain the same result, which means that the two diagonals of this isosceles trapezoid are equal in length. Particularly, they are both 109 in length. Okay? Next. Let us have number 8. Okay, the cross-section of a water trough is in the shape of a trapezoid with bases measuring 4 meters and 14 meters. Now, what is the length of the median of the trapezoid? Now, for our solution, let us draw a figure of an isosceles trapezoid or simply trapezoid. And we assume that this is a trough. A trough. Okay? Whatever you pronounce that. Okay? So it means this thing is in the shape of a trapezoid. And in this figure, where are those bases? Basically, those two horizontal sides. The longer base is the upper base and the shorter base is the lower base. Yun. Okay? The longer one is 14 meters while the shorter one is 4. And we are looking for the length of the median of this quadrilateral. Now, where can we find that median? The orange segments connecting the midpoints of these legs. Okay? Now, how do we compute for the median? This is the formula, which is actually the average length of the two bases. Yun. So by substitution, we can compute for the length of the median. Yun. And that is 4 plus 14 all over 2. The answer is 9. So this is 9 meters is the length of this segment, which is the median. Okay? Next. How about number 9? Okay, at this point, we will now discuss the last type of, or the last kind of quadrilateral. And obviously, I'm referring to a kite. So in example number 9, we are now considering a problem that relates to kite, whose name is quadrilateral KLMN. Okay? So the problem number 9 is asking for the area of this kite with this name if, okay, obviously this is a diagonal whose length is 12 and the other diagonal has a length of 16. And they are both in centimeters. So how do we compute for the area of a kite? So for our solution, let us draw a kite and let us assume that this is quadrilateral KLMN. Okay, so segment LN and segment KM are the given diagonals. We can compute for the area of a kite using this formula, which is half of the product of the diagonals. So basically, we directly substitute the given lengths. So that is 1/2 of the length of segment LN and that of segment KM. So plug in their equivalent values or given values. So this is for LN it's 12 and for KM is 16. Now simplifying this resulting expression, you will notice that the area of this kite is actually 96 square centimeters. Okay. Next. Number 10. Using the same figure in example number 9, if the area of the kite KLMN is 36 square centimeters and KM is 12, how long is the length of the other diagonal whose name is segment LN? Okay, we again refer to the same figure and let us use the same formula, but this time we need to find out or we need to compute for the length of one of the two diagonals. Since the area is already given as what? 36 square centimeters. So using the formula, we plug in those given values. One is the area of a kite, 36, then 1/2. Copy this part, 1/2. Then LN is the one we're looking for, so you just rewrite that. But when it comes to KM, we have its equivalent from the given, which is 12. Ayun. Then you manipulate, now you solve this equation, solve for the value of Ln, and what do we have? Okay. So you do the cross product method. 2 times 36 is 72 equals Ln times 12. So basically, we divide both sides by 12 so that we can get the value of Ln. And that is equal to 6. So what does this mean? It means the length of the other diagonal, whose name is segment LN, is 6 centimeters. Okay, I think this will be my last example. And we'll see you next time.